In this video, we will discuss what we call game theory. So we'll start with the most simple games that we describe, which are static games of complete information. These types of games are defined by n number of players, and in general, we'll start with 2 because that's the easiest case of strategic interaction, a strategy set for each player, and then a set of outcomes or values based on the combinations of strategies chosen. And again, we're going to start with simultaneous non-cooperative games of complete information. So the decision makers will be choosing simultaneously and independently, and they know the number of players in the games, what the strategies are, and what the outcomes are. All right, so one example of a game like that we studied was the Cournot oligopoly, where 2 oligopolists simultaneously and independently chose their quantities. A common example of this static game of complete information, non-cooperative, is known as the prisoner's dilemma. And there's a number of formulations of this problem, but one I like comes from a British game show called Golden Balls, where 2 contestants have earned a prize, and at the end, they have the choice to either split it or try to steal the entire prize for themselves. All right, so here's how it goes. There's 2 players, all right, number of players is 2. Their strategy set, each can try to split or steal, and they're choosing at the same time. And then there's a set of values based on the combination. So the outcomes are, if both choose steal, each gets only 1% of the total prize or walks away with very little. If both choose split, they'll each get 50% of the total prize. And if one chooses steal while the other chooses split, whoever chose steal will get 100% of the total prize. Right, so in order to analyze solutions to these games, it's useful often to visualize them. So we'll talk about 2 ways that we can visualize these types of games. One is what we call a payoff matrix, which is below, and then we'll also talk about game trees, although game trees are really more useful once we talk about dynamic games, which have a time element. Okay, so let's start with the matrix representation. So we've got player 1, and we're always going to list player 1 vertically or in the rows, whichever one you want to think of this. And then player 2 will be along the top or in the columns. So player 1 has the choice whether to split or steal. Player 2 is choosing whether to split or steal, and they're doing so simultaneously and independently. So there's 4 possible outcomes again, which we listed. If both choose split, 50-50. Here, one other note is that player 1's payoff will always be represented first, and then player 2's payoff, so left and right. So if both choose split, 50-50. If player 1 chooses split and player 2 chooses steal, then the player who chose split, player 1, gets nothing. The player who chose steal, player 2, gets the entire prize. All right, if player 1 chooses steal and player 2 chooses split, then player 1 steals the entire prize. And then I had changed these to 1s actually, so I should change that in the matrix just so there's no ties for now. But if they both choose steal, they both essentially get nothing. All right, so here is the game, and then we can also represent this game in what we call a game tree. So player 1 chooses whether to split or steal. Player 2 chooses whether to split or steal. And then we've got this oval around player 2's choices, which is indicating to us that when player 2 makes this choice, they don't know whether they're right here or right here. Or in other words, they can't tell whether player 1 has chosen split or steal because it's simultaneous. Right, and then we've got, again, our payoff, split, split, 50-50, split, steal. Here, player 2 has stolen, gotten it all. Steal, split, Here, player one has stolen, player two tries to split, so player one takes it all, and then steal, steal, both get nothing. Right, so we'll talk about the solutions here. There's actually a few different types of solution methods to these types of games. So we'll go through each type of solution method and talk about them. One more formulation, just so we have some practice representing these as matrices. So another prisoner's dilemma type of problem. We've got two thieves that are being questioned, assume that they have committed a crime. They can either stay silent or betray their partner in crime. If each stays silent, there is limited evidence to prosecute on, and each receives a fine of 1,000. One stays silent while the other betrays. The thief who betrays will get off without a penalty, while the other receives a fine of 5,000. And if both betray or confess, they each get a fine of 4,000. And the exact numbers aren't too relevant. The only thing that matters really is kind of the ratios. So the exact payoffs aren't too important. But what we can do is represent this once again as a payoff matrix. So player one can stay silent or betray. Player two can stay silent or betray. And then here we have our payoffs: silent, silent, betray, betray. And then here we have player one has stayed silent, player two betrayed them. So player one gets the entire fine. And then reverse for player two. Here player one betrays and gets off without a penalty, while player two stays silent, has to pay the entire fine. Right, we can represent this as a game tree as well. Again, we won't spend too much time on the game tree representation yet because it's more useful in games where there's a time element or a sequence of moves. But here, player one is silent or betray. Player two picking silent or betray, and then they don't see what player one has chosen. So player's two choices is made in one information set here, where all player two knows is that player one could have stayed silent or betrayed, but doesn't know which. So let's talk quickly about some solving techniques. The first solving technique we'll talk about is strategic dominance. Just quickly, a couple definitions. A best response is a strategy which maximizes an individual's payoff, conditional on the strategy choice of an opponent. So given what your opponent is going to do, what is the best strategy for you to pick or the highest valued? For player I, a strategy is defined to be strictly dominant if the value of choosing that strategy is greater than the value of any other strategy, no matter what your opponent chooses. Or weakly dominant is if it's greater than or equal to that value. So we could have some ties in the split steal game. Originally, we had some ties. If there's ties, we have what we call weak domination. And then finally, a strategy is strictly or weakly dominated if there's at least one other strategy such that the value of that alternative is always greater for strictly dominated or greater than or equal to for weakly dominated. So we're going to propose that a rational decision maker will never play a strategy which is strictly or weakly dominated. Again, what that means is there's at least one other strategy that no matter what your opponent picks, you're always better off playing the alternative. Right? So a rational decision maker will never play a strictly or weakly dominated strategy because there's at least one better strategy or higher valued strategy, no matter what the opponent does, and they know that. Also, a rational decision maker will always play a dominant strategy if it exists. So remember, a dominant strategy means that the value of that strategy is always the highest, no matter what the opponent picks. All right, so let's return to the split and steal prisoner's dilemma game, but we're going to avoid ties here by just giving a payoff of 1-1 for steal, steal. So let's only consider player one for now. Player one knows that player two has either split or steal. Let's assume just for a minute that player 1 believes that player 2 is going to split. So let's look only at this column, right? Ignore the steal column for a second. Or what if player 1 had some way of knowing that player 2 had split for sure? What should player 1 do? Well, player 1 would get 50 for split or 100 for steal. And so conditional on player 2's decision to split, player 1 would be better off stealing. Remember, for player 1, we're looking at the first payoff. All right, well, what about if player 2 instead chose to steal? Player 1 would get 0 for a choice to split, or if they chose to steal, would get 1 and is better off stealing. So what we can say here is that no matter whether player 2 chooses to split or steal, player 1 is better off stealing. We can say that the strategy of split for player 1 is in this case strictly dominated because steal is always strictly higher valued than split. And because there's only 2 strategies and one is strictly dominated, we know that steal is a strictly dominant strategy. So what did we say about a rational decision maker? A rational decision maker will always play the dominant strategy if it exists. We can say that rationally player 1 should always choose steal. All right, what about player 2? Suppose that player 2 knew somehow that player 1 had chosen split. So now we're looking at this row right here where player 1 chooses split. If player 2 chooses split, player 2 will get 50. If they choose steal, they will get 100. And so if player 2 knew somehow that player 1 was splitting, player 2 should steal. And again, for now, we're assuming that these people care only about their own individual payoffs. We probably won't have time to get to types of problems that relax those assumptions, but there are problems with what we call altruistic or other regarding preferences too. All right, so then what about if player 2 had some way of knowing that player 1 is going to steal? So that's this bottom row. In this case, if player 1 is stealing, player 2 would get 0 to split or 1 to steal, and therefore should choose steal. So once again, the strategy of split is strictly dominated for player 2. Steal is the dominant strategy. What we can say is that this game has a dominant strategy equilibrium, which is steal-steal. We can also see that the payoffs in this dominant strategy equilibrium are much worse than if they were able to cooperate or split this prize. So this is why it's called the prisoner's dilemma. There is a unique equilibrium in dominant strategies, which is strictly worse than the optimal play. So let's look at our other formulation of this prisoner's dilemma, the one with negative payoffs or fines for having committed a crime. So let's once again consider the choice of player 1. Player 1 can stay silent or betray. Suppose that player 1 knows that player 2 is staying silent. What should player 1 do? They would get -1 to stay silent or 0 if they betray. Once again, we're assuming that they care only about their own payoffs, not about the other payoffs or the ratio of the payoffs or anything. They only care about strictly the number or the value that they get. 0 is more than -1, so conditional on the partner staying silent, player 1 has incentive to betray. What about if player 2 is chosen to betray? Player 1 would get -5 for staying silent or -4 for betraying. Once again, should betray. So player 1 has a dominant strategy, betray. No matter what player 2 does, player 1 is better off betraying than staying silent. 0 is more than -1. -4 is more than -5. Player 1 should always betray or has a dominant strategy to betray. About player 2, if player 2 knows that player 1 is staying silent, player 2 would get -1 to stay silent or 0 for betraying. And therefore, they should betray. If player 2 knew somehow that player 1 was betraying, they would get -5 to stay silent or -4 to betray. So once again, player 2 has a dominant strategy, which is betray. There's a dominant strategy equilibrium of this game, betray, betray, and we can see that the payoffs in that dominant strategy equilibrium are lower than if they had cooperated or stayed silent. So why don't they stay silent? Once again, in this case, each player would have an incentive to deviate. If player 2 was staying silent, player 1 would be better off betraying. If player 1 was staying silent, player 2 has incentive to betray. So we end up at betray, betray. Right, so the strict dominant strategy equilibrium is a useful tool for us because we know that we can say generally that rational decision making involves always playing dominant strategies if they exist. Of course, we'll see that as games become more complex, or even these types of games don't always have strict dominant strategy equilibria.